Hello everyone and welcome to Lecture. Today I'd like to talk about what's called Propositional Satisfiability. This is the idea of what it takes to satisfy a certain proposition and is directly related to the idea of forming an axiomatic system, which is essentially what all of mathematical theory is based on. So the idea is a little bit later on in discrete mathematics, what we'll be studying is different things that you can do with certain axiomatic systems, how we can kind of build up certain sets of numbers, so set theory. This is all built from propositional and predicate logic. And one of the important questions is what does it take to satisfy a certain proposition? So this is kind of what we'll be talking about today, propositional satisfiability. And we'll begin by giving the following definition. We define and say that a compound proposition is satisfiable or is said to be satisfiable if there is a certain assignment, or we'll put there is an assignment of truth values and truth values and false values that make it true. And there doesn't, there may only be one possible combination of truth values and false values. So, for instance, let's say I have some very compound proposition that depends on like 3 statements. So we'll say like P, Q, and R are all input statements to some compound proposition, heart. Of PQR. Well, we know from before that we need to list all possibilities here in this case, and what we're going to have, we have to list 2 cube total possibilities here. So we're going to have true, 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 false, 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 false. Q is true, true, false, false. True, true, false, false. And then lastly we go true, false, true, false, true, false, true, false. And this gives us all possible input propositions to any given proposition. So the idea is that, let's say this input proposition is such, just for example, such that it's false everywhere except one column. It's false here, false here, false here. Maybe this, or these input values. This P is false, this Q is true, this R is true. This makes this heart say true, but everywhere else it's false. And we would say that this heart is a satisfiable proposition. Or, alternatively, you could say maybe it's true for this right here and true right here. This satisfiable is an existent statement. It says there exists some assignment of truth values such that the proposition itself is true. So like this is the previous thing that I wrote is an example of satisfiable. This is an example of satisfiable. But let's say we have some other proposition, I'll call it star of P, Q, and R. If there are no combinations of truth values that make it satisfy the proposition, so everything is false, this is false. Everything here is false. If any input combination of truth values make a proposition false, then we call it unsatisfiable. So star is unsatisfiable. We'll just abbreviate that US for short, for unsatisfiable, the opposite of satisfiable. So what you can see then very, very quickly is, hopefully, is that an unsatisfiable proposition is the same thing as a contradiction. By definition, these two things match up. A contradiction is the same thing as an unsatisfiable proposition. But that doesn't mean that a satisfiable proposition is a tautology. That's not true. Because this is an example of a satisfiable proposition right here that is not a tautology. There are only two input combinations that make this heart proposition true in this example right here. This is a good example showing what we mean by a satisfiable proposition. And I guess the truth of the matter is that for like 3 input propositions, we don't have to worry too much about satisfiability, but even for even with 3, our truth table, if we're going to approach it using truth tables, are growing very, very fast. So the problem here is that the more input propositions we have, the more we have to, the more difficult it becomes to use a truth table. And past a certain number, it's almost impossible to do this using a truth table. So we're going to have to rely on logical equivalences, but theoretically speaking, we can use either method. So we can determine satisfiability can be determined using either of the 2 methods we've gone over before. So either, say, one truth table or logical equivalences. The idea is that truth table, because the truth table grows very, very quickly with the number of input propositions, this is not always the best way of figuring this out. What's a better way very often of figuring this out is by going through and using logical equivalences and logically deducing whether or not something is satisfiable, whether or not there exists some combination of P, Q, and R that, or however many input propositions you have that will satisfy the statement S. So let's see this for a couple of examples, some specific examples, so we can kind of like wrap our minds around this. That's what we want to kind of do always. So the first example I'll do is the following. We'll talk about this proposition S. This is the proposition P or not Q, and Q or not R, and R or not P. And we'll do it using both methods so that we can kind of see exactly what we're talking about here. And the first method from before was the truth table. So doing out this proposition using a truth table by hand would be relatively long, and I don't want to do that right now because we know how to compute a truth table at this point, and we know that because there are 3 input propositions here, it's going to be relatively large and relatively complicated to go through and do. I mean, I guess if you want to see how to start it out, you would do exactly what I did up here, where you do 3 columns for one for P, one for Q, one for R, and then you'd have to go through and do P or not Q, Q or not R, R or not P, and then do an AND operation between each one of those columns. That's the correct way of doing this truth table for this statement. But what I'm going to do is show you a trick that you can kind of use. You're going to want to know how to do truth tables by hand for the exam, but I will show you a trick that you can use for your homework to try and help you out a little bit and check your work. There's a truth table generator online on the Stanford website, Stanford College, and you can find this just by Googling truth table generator, and this can be used to generate a truth table for any number of input statements. So you can use this in kind of helping you in your homework, but you should know and understand both methods. So what we want to verify is the previous statement. Remember, we want to verify or figure out the truth table for this statement: P or not Q, Q or not R, and R or not P. This is the logical statement that we want the truth table of. So I'm gonna put this right here, put this right here, so we can kind of see both. So we want to do P or not Q, and then we want to do an AND operation between that and Q or not R, and then lastly we want to do an AND operation between R or not P. And very clearly we see all these possibilities right here from our truth table. These are match up with all of our input possibilities for P, Q, and R. And what we see is that from the truth table, this is a satisfiable proposition because there are 2 possible inputs that give us a value of truth and satisfy this proposition. But the only values that do this are the values P is false, Q is false, and R is false. And then so this is one possible solution. Another possible solution, solution 2, is the solution P is true, Q is true, and R is true. So the truth table tells us that this is a satisfiable proposition, and it gives us all possible solutions to this satisfiability problem. This is nice, and it works especially well for a small number of input statements, but when you start chaining together a larger and larger number of input statements, this is going to become unwieldy. And if you have, say, even maybe 10 to 20 input statements, generating this truth table is not easy. It's not nice. It won't look nice when you go through, when you like write the table down, because it's so long. And if you go even larger than that, let's say 100, 1,000 input statements, this is going to take a while to generate and to process this information. So ideally, we would have a better means of going through and figuring out the satisfiability of a proposition. Specifically, what we need to do here is use our logical equivalences, if we can. And this is how we do it using logical equivalences. So this is the truth table method that I've shown. Method 2 here is to go through and use a logical argument. So we say, okay, so how can we satisfy this? How can we make S true? So if S is true, then we have to have that either P is true or Q is false. This is what this is saying right here. And we also have to have, so we have an and, either Q is true or R is false, and we have to have that R is true or P is false. Now remember, this method too doesn't rely on truth tables at all, just using the logical operators and arguing based on them. So the idea here now is that the only solution that we have is, well, if P is true, then we take P to be true, which means P cannot be false, which means the only way to satisfy this is that R is true, and if R is true, then R cannot be false, which means the only way to satisfy this is that Q is true. So that gives us our first solution, or that P is true. So P, Q, and R is true, or are true. This is our first solution from before, or our second solution from before. This is solution 2. And the other way of arguing for the other solution that we get is that, well, the only other way of satisfying this one is having Q be false. So if Q is false, then that means that if we go here, Q cannot be true, which means the only way of satisfying this guy is that R is false. And if R is false, that means the only way of satisfying this one right here, R can't be true, so P must also be false. And we get that P, Q, and R are false, or are all false, which matches our solution 1 from before, from the truth tables. So really, method 2 here is the faster method of using, because the idea is that we just decompose into the fundamental building blocks of the statement and make an argument based on just logic or logical equivalences. The idea here is that any combination of statements can be used to do this, and this is kind of the idea behind using logical equivalences to figure out the solution to a satisfiability problem, as opposed to doing the truth table. You'll be expected to know how to do both, but the idea is that this method too is often the quicker method to use, especially if you have any more than 2 input statements. As a somewhat more advanced application of satisfiability, we can think of what's called the Sudoku Puzzle. This is a really good example. Is in the book, but I'm just going to quickly talk about the Sudoku Puzzle as another example of satisfiability, and I'll probably add another page to this as well. This is, and many problems are like this because they can be rephrased into a logical satisfiability problem, but the Sudoku Puzzle is a good example because it's a puzzle that most people, I think, have heard of and kind of know of. And if you don't know what a Sudoku puzzle is, I'll talk about it right now. It's you basically have a grid of grids. So we have nine grids, and in each one of these grids we have another smaller grid of 9 cells. And in each one of these I just finished drawing this, and I'll continue in a second. And so Sudoku puzzles themselves as well can be written not just with 3 by 3 grids, but you could do in general an n by n grid if you want to. That's perfectly fine. But the idea is the following: to fill in numbers in this grid, and you have basically 3 rules. You have to make sure that you have numbers 1 through 10 in each one of these boxes. So you have to have a 1 through 10 in each one of these boxes. You have to have a 1 through 10 numbers 1 through 10 in each one of the columns, so up and down in every column here, and a 1 through 10 in each one of the rows, but no repetition. So for instance, like I could have 1, 2, 3, 5, 6, 7, 8, 9, 10, something like this. This is fine. Oh wait, sorry, no 10. I went a little bit crazy there. 1, 2, 3. I'm missing a 4 here. So there's integers 1 through 9. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So we have every integer in this box. But now I'm restricted in this row right here, and in all of these columns right here. And that I have 1, 2, 3. I could have a 4, a 5, a 6. 7, 8, 9, like this. But the idea now then is that I'm also restricted here. So this is 1, 7, 8. I could have maybe like a 2, 3, 4, 5, 6, 9, say. This should be okay. But then I'm also restricted here in that I have 2, 3, 9. So the idea is that I'm constricted. I can't have a 2, 3, 9 in this one right here. So the goal is to fill in everything, every single box here, making sure that each one of these boxes has 1, 2, 3, 4, 5, 6, 7, 8, 9, but no repeating numbers in any one of these individual boxes. And same thing for each individual row and column in this puzzle. So there are varying degrees of Sudokus. The more difficult Sudokus form a satisfiability problem with less solutions than the easier Sudokus. So some Sudokus are relatively easy with multiple solutions, but other Sudokus are harder, and there's only 1 or 2 solutions to the Sudoku itself. So this is the Sudoku example. And the main way that we're going to talk about forming this as a satisfiability problem is by making a number of different propositions that have to be satisfied and chaining them together with an AND statement. So the idea first is that I want to introduce some notation that we'll use a little bit later on in the course. And this is related to before. So I said before that we have that if I have, say, let's say I have n propositions, so P1 through Pn. I talked about how the statement for all I, Pi is the same thing or logically equivalent to the statement P1 and P2 and P3 and so on and so forth all the way to Pn. Now we also have another nice notation for this. It's similar to a summation notation that you might see in calculus, which is to just put a big AND symbol, one big AND symbol, starting with I equals 1 up to n Pi. This stands for the AND operation between n statements, P1 and P2 and P3 and P4 and P5 all the way up to Pn. Similarly, we can write for, this is only for finite, but it also extends to infinite, as we will see later on. If I put there exists, remember this is there exists an I such that P of I, we could rewrite this as the OR statement on all of the P of I. So what this notation means right here is the OR statement for I equals 1 to n of all pi. So this means p1 or p2 or p3 and so on and so forth all the way to pn. So this is just an important notational thing that is used in the book and is also used in other areas for doing an or an and. But the main thing here that we can do, the main goal, is that we now have, if this is our Sudoku puzzle, we now have the following proposition for each individual cell in this Sudoku puzzle. We'll define it as follows. We'll say the proposition Pijk is the following proposition. This is logically equivalent to, it's the same thing as the proposition that row I and column J contain number k. And remember, so in the Sudoku puzzle, we have a typical Sudoku puzzle, we have 9 rows and we have 9 columns. And if each individual if we have in each individual section, we have 9 possibilities, so 9 possible numbers to fill a box with for each one of these options right here. That means there's a total number of possibilities here. The total number of possibilities that we have is 9 times 9 times 9, which ends up being 729 total possibilities in terms of how we can distribute these values. So this gives us a very large large number of propositions, right? The idea is that any Sudoku puzzle or any possible solution to a Sudoku puzzle consists of 729 input propositions. A great number of these are false, but the idea is that this is the total number of input propositions. So doing this out on a computer is even difficult. It'd be large to do. You can do it. It's possible to do. And write a computer program that solves Sudokus, but it's definitely like a large task. There's a huge amount of input propositions. So the idea is that if you think of all of these propositions, Pijk, as input propositions, you have 729 total input propositions, which means the total number of possible solutions to the Sudoku puzzle is 2, right? 2 to the 729. Because those are the total possible ways of filling in the puzzle. So this is a very large amount of ways, and the idea is that it's not feasible to do. But what we want to do is kind of try to use logic to eliminate a number of different possibilities. And I'm not going to go through and solve the Sudoku puzzle, but I'm going to show you how the Sudoku puzzle is itself a propositional satisfiability problem for a number of different exact propositions. Specifically, we have 4 exact propositions that we need to satisfy. The first proposition that we need to satisfy, we'll call it 1, is that, you can call this P1. Maybe not P1, maybe Q1 is a little bit better because I'm already using P. So we'll call this Q1. We'll call Q1 the proposition that every row must contain every number. Well, this is logically equivalent to the statement that for all I, where I is representing the row, and then for every possible filler number that we can put into the box, there has to exist some column, we'll call it J, such that P, I, J, K is true. So what this is saying is that for every row I, and for every number that we can fill into that row K, there has to exist a column J, such that K goes into the ijth position, or K goes into the jth row, or the jth column. And the book writes this a different way, but it's really the same statement that this for all I is I from 1 to 9. This for all K is, again, K ranges from 1 to 9. Is the intersection, is the intersection from I equals 1 to 9 of the intersection from K equals 1 to 9 of the existence statement. So it's an OR statement on each J. So from J equals 1 to 9 of P, I, J, K. So this is the first thing that we need in a Sudoku puzzle. We need that every row must contain every number. We'll call it Q2, the next statement, and it'll be very, very similar to Q1. It's that every column must have a number, well, one of the numbers, or sorry, every column must contain every number. And again, just like before, this is very similar to the last statement, but now we have to do a for all statement on each column. So it's for all J, we'll say, for every possible number K, we have to be able to find a row I, there exists in a row I, such that K goes in the ijth component. This is saying for every column and for every number K, we should be able to find a row I such that K goes in the ith row in this column J. So again, in terms of the intersection notation that we introduced earlier, this is the same thing as saying I from 1 to 9. The intersection of I from 1 to 9 of the intersection from K equals 1 to 9 of the union from I equals 1 to 9 P, I, J, K. So this is Q2. This is the statement that every column must contain every number, written like this in terms of logical notation, but really this is just this same statement right here. This is the second thing that we need to have a solution to the Sudoku puzzle. The third thing we need for a solution to the Sudoku puzzle, we'll call it Q3, is that each of the 9x9 blocks must contain every number and this is a little bit more tricky and delicate to write down than the first two, because we need to kind of effectively and efficiently write this down using what we talked about before. So what we're going to do, and the way that the book does this as well, is it uses kind of, you can think of them almost as like as helper variables to efficiently and effectively denote each one of these blocks and number off each one of these blocks. Specifically, they do the following. They talk about how, and the book doesn't do that. It does an okay job of explaining it, but we really kind of want a little bit more in-depth explanation. That's what I'm going to give right here. So it numbers each one of these blocks using variables s and r. Specifically, this one it calls S0, R0. That's this first one right here. This one right here, this block right here, this you could say this row of blocks and this column of blocks is S1 for this column. And this column right here it calls S2. This column right here it calls R1, 0, R1, and R2. And then the idea is that it looks at the relationship between these numbers S and R to the actual physical location in this case 1 by 9 and 1 by 9. So we essentially have 9 possible real columns here in each one of these, for every row, and for every column we have 9 possible rows in the Sudoku puzzle. So the idea is that these things are numbered by so S goes from 0, 1 to 1 or 2. It can be 0, 1 or 2, and R can be 0, 1 or 2. And the idea is what we have to do is we have to say that for every S possible value of S and every possible value of R, we have to have the statement that every single number, there exists a row and a column in that specific block, or restricted to that specific block. So specifically, they then break down to saying that in each one of these blocks, we also have another, we have a 3 by 3 grid. So what they call is, they say that M, in each individual block, M is the thing that denotes. So M is the thing that denotes the row in each 3 by 3 subgrid, and N is the column in each 3 by 3 subgrid. So M can be 1, 2, or 3, and N can be 1, 2, or 3. S can be 0, 1, or 2, and R can be 0, 1, or 2. And so this statement Q3, is logically equivalent to the statement then for all R and for all S. So this gives us every single one of these grids right here for all numbers K. We need to be able to find a position M and an N, so an M and an N, such that the number K is inside, or fills in the mnth position in each subgrid. And this is why we have for all R, for all S here. This gives us each one of these grids right here. So we have to have then that P of, and this might seem a little bit confusing at first, 3R plus M, 3S plus N, K is true. This proposition is true. So let me explain this a little bit. The main idea here is that this is saying that K goes into the position 3R plus M, 3S plus N. You want to think in terms of the actual number of 3R plus M and what that is for each individual possible value of R and of S. And the idea here is the following. If we so I think I mislabeled this up here a little bit. Sorry, it's not a big mislabeling, but it is a little bit. So this should be R right here, and this should be S. I apologize for that. But that makes more sense right here. So let's consider, for instance, R S equals 0 and r equals 1, say. So that's this block right here. Well, if s equals 0 and r equals 1, for each individual possible value of, we're in this block right here, and then for each individual value of m and n, right, what we have is that, so if so s is 0, then we have that this value right here is 0 plus m. The possible values of 0 plus m are 1, 2, or 3. And if s is, this is if s is 0. So 0 plus n of 1, 2, or 3, which directly corresponds to this right here. And then if r, so r is equal to 1, we have 3 times 1 plus m. This is equal to 4, 5, and 6. So this corresponds to values 4, 5, and 6 right here. 4, 5, and 6. And this corresponds to 1, 2, and 3. So we're 1, 2, and 3 right here. So really what this is saying is that in this, if you just look at the statement, for instance, for all k, there exists m and there exists n, such that, you know, in this case right here, we have to do this for all r, and for all s, but just in this subcase right here, we have the subcase of the square, this first square right here, in the row s equals 0 and column r equals 1. We have to have that p of, it'll be 3 plus m and 3s, so an n guarantees us that this block right here is filled with every value, possible value of k. So really what this is the same thing as is saying, so the statement Q3, remember, we're talking about here, is logically equivalent to the statement of the intersection for r from 0 to 2, so r from 0 to 2, of the intersection r equals 0, or s from 0 to 2, and k from 1 to 9, then m from 0 or 1 to 3, and n from 1 to 3 of the statement p 3r plus m 3s plus n and k. And just like before, like I said, for this just one example of this block right here, we have to include the and to do it to every single individual block of this statement. So this Q3 right here is just the statement that every 9x9 block, or sorry, it's not every 9x9 block, but every 3x3 block must contain every number. So good. So we have statements 1, 2, and 3, and there's actually one more statement that we need to include, and that's a statement that deals with the fact that we can't have any more than one number in every cell. So every cell has to contain one and only one number that can't match up, or can't be doubled. So the last statement, we'll call it Q4, is that no cell contains more than one number. And this statement can be listed as an implication. Is the statement we say for all I for all j, and then we say for all k, and I'm going to use k prime as a dummy index. But for all I, for all j, for all k prime, so we have to first say that we have that. So let's assume this is only over when k is not equal to k prime. So when k is not equal to k prime, then we have to say that if k is in cell ij, then what has to be true? So if k is in cell ij, we have to ensure what? So it turns out that if k is in cell ij, then we have to make sure that k prime is not in ij. Right? This is for all k and k prime, such that if k is not equal to k prime, then if k is in cell ij, then k prime is not in ij, because k prime is not equal to k from assumption. This is a for all statement right here. So this statement right here is logically equivalent to this statement right here, which means we can then also say that if you want to do an intersection right here, this is the intersection for I from 1 to 9, intersection for j from 1 to 9, intersection for k to 1 to 9, and intersection k prime from 1 to 9 of this statement right here. So it's the statement k is not equal to k prime, and if k is in the ijth cell, then k prime is not in the ijth cell. This is a negation of k prime being in the ijth cell. So this is the fourth statement, and it's the last statement that we need to really define the logical satisfiability problem that the Sudoku puzzle represents. So then the idea now is that solving a Sudoku puzzle is the same thing as solving the satisfiability problem. For the statement Q1 and Q2 and Q3 and Q4. Now, I guess the problem with doing such a solution, solving such a satisfiability problem, is that there's a lot of possible solutions, right? If there are 729 input propositions, like we talked about before, so 729 possible values for p, I, j, k. Well, so there are 729 total possible p, I, j, like possible things that we could put in here, and for each one of these there are two choices. We have a total of 2 to the 729 total possible inputs to this satisfiability problem, which is a very, very large number, and it's a very, very hard, in general, thing to solve. You can do it using the computer, but even that very often takes a long time, and you need to be very, very careful with it. So that's why it takes a while to actually make a good Sudoku, and to grade Sudokus based on level of the difficulty for the problem. But in general, I think this is a very, very good application of predicate logic, and showing how predicate logic applies to satisfiability problems in general. But I think this is good enough for the lecture, And I thank you very much for tuning in and hope you had a fantastic day.